Meeting you, sir. Hope to talk to you soon.
Thanks, Steve. Appreciate it.
All right, everyone. Welcome back to our seminar. Today, we're going to continue our so-called PRE series with Mr. Karl Fleming. After having Dr. Nathan Sue's views from the NRC, we're going to continue with Karl Fleming, who's a pioneer in the development and application of PRE technologies, mostly on the industry side. So his methods and data analysis for the PRE modeling of common cause failures, including the beta factor and multiple Greek letter methods, are products of his early work at PLG. He has extensive experience in performing and directing major PRE projects on high temperature gas-cooled reactors and pressurized water reactors. He was the principal author of the LMP guidance documents, including NEI 1804 and some of the pilots. He is, up to today, the chair of the SME-NS Joint Committee on Nuclear Risk Management Working Group on Advanced Non-Light Water Reactors, which is responsible for the PRE standard, joint SME-NS standard. And lastly, he was inducted to the National Academy of Engineering in 2020 and became an ANS fellow in 2018. Karl, you have the floor.
Yeah, thank you very much, Mihai, and welcome everybody. I look forward to talking to you today about the licensing modernization project. And as far as your last speaker is concerned, I had the pleasure of working with Nathan Sue for many years when we were both working at Pickard Lowe and Garrick, and which became PLG. So I'm sure you got a very good presentation from him because I've heard his talk. So hopefully I can live up to his standards. What I'd like to do is figure out how to do my slides here. I'm going to start by reviewing some of the limitations of the current regulatory framework for nuclear power plants as it pertains to licensing advanced non-light water reactor plants. And I'll just go over some of the key differences in the safety characteristics of the advanced non-light water reactors in contrast with those with the existing reactors. That's important because those safety characteristics of light water reactors are baked into the regulations, and it's created a big challenge for moving forward with non-light water reactors. Licensing modernization project was put together to solve this issue, and I'll talk about that as well as how the probabilistic risk assessment technology fits into that process. Going into the safety features of existing light water reactors, operating light water reactors, we're talking about the vast majority of the radionuclides are contained within zircaloy clad uranium dioxide fuel elements. They must be covered in water, and that has to be subject to heat removal to prevent clad oxidation, fuel melting, hydrogen production, and those types of things. So that's the characteristics that really came out of the Naval Reactors Program. In order to support the safety case for the existing reactors, you have to maintain the integrity of the reactor coolant system, the coolant system pressure boundary, and you need to maintain water levels in the reactor and the reactor vessel, and take heat out of the reactor coolant system to prevent core damage. And that makes the systems vulnerable to so-called loss of coolant accidents. To keep these safety functions safe, there's a reliance on active systems that are dependent mostly on electric power to maintain a safe core configuration. And the safety case is heavily dependent on having a external leak-tight containment structure around the reactor coolant system to prevent and mitigate the releases that might occur from the reactor coolant system. All these safety characteristics are baked into the wording of the regulations and the general design criteria for nuclear power plants. Along come the advanced non-light water reactors that bring in Very diverse types of, many different types of advanced reactor concepts with different materials, different types of fuels, different types of coolants, and for the thermal reactors, different types of moderators. In some cases, the fuel is dissolved in the coolant, like in molten salt reactors. Different strategies to contain the radionuclides, more of a functional approach to containment rather than a building, leak-tight building on the outside of the plant. Much greater reliance on the use of inherent and passive means to perform safety functions. And this gives rise to smaller, cheaper, and less complex reactors than light water reactors. That's the good news. The bad news is there's been a lot of impediments to advancing these technologies because of what I covered on the previous slide, that the existing regulations are very, very light water reactor centric. And uncertainty in the cost and time required to license the plants has really been an impediment for advancing the technologies. The licensing costs and risks in the licensing process really offset the benefits in terms of having a smaller, cheaper, more inherently safe plant. So that's the situation that gave rise to the advent of the Licensing Modernization Project, or LMP as we call it. LMP is an industry-led project to modernize the licensing process for advanced non-light water reactors. It uses a risk-informed and performance-based methodology to select and evaluate licensing basis events, to achieve the safety classification of SSEs, as well as come up with the safety requirements for those, design requirements for those, and also to evaluate the adequacy of defense in depth. The effort was led by Southern Company, which led the development of this project with cost sharing with the U.S. Department of Energy and the nuclear industry. Most of the funding comes from the U.S. Department of Energy. And after a number of years of working on this, it gave rise to a guidance document published in NEI 1804, which has now been endorsed by the NRC in a regulatory guide 1.233. There's a full set of documents on the LMP that can be found on the website listed on these slides. And I provided a copy of these slides to Mihai, and I'm sure that anybody who wants access to those, you're free to get a copy of those slides and use that to get to this website. The background here is that way back in 1998, the commission issued a policy on risk-informed and performance-based regulation. It was exploring the idea of a logical prioritization of challenges to better allocate the resources for these advanced reactor technologies. They wanted it to be risk-informed and performance-based. Risk-informed requires a little bit of definition here, because if you look at the words, it might just suggest that, well, you're informing your decisions based on risk. Well, it's a little bit more than that. Former chairman of the Nuclear Regulatory Commission, Shirley Jackson, who left the NRC and became the president of one of those North Carolina universities. I don't know if it's North Carolina State or University of North Carolina. But risk-informed means it's a balanced approach of deterministic risk and deterministic principles and risk insights from a PRA. Performance-based means that we're going to use measurable or quantifiable metrics to determine how safe is safe enough, as opposed to arbitrary process-based regulations as it's currently framed in the regulation. The focus of the methodology, the LMP methodology, is to produce a systematic, reproducible, and robust integrated process that's for identifying the safety significant licensing basis events appropriate for each non-light water reactor design based on a design specific PRA. And while the PRAs and the safety cases are very reactor design and technology specific, the process we invented here in LNP is technology inclusive. It really covers all the reactor technologies. We also want to use a systematic process to select the safety classified SSEs and develop the performance requirements for the SSEs. We also want to establish the risk significance of individual licensing basis events, as well as the collection or the integrated risks of the facility. And we also want to demonstrate enhanced safety margins consistent with the Commission's advanced reactor policy. We want to balance both deterministic and probabilistic inputs. The reason why we want to keep the deterministic principles in play is that there are limitations of PRA. We can't make it a full risk-based process. So we supplement the risk insights from a design-specific PRA with deterministic principles, and that comes into play as in the defense in depth part of this process. The cost of a nuclear power plant in the United States really comes from the special treatment requirements for the safety classified SSEs. So what we want to do in the LNP process is come up with more performance-based requirements that are linked to balancing the prevention and mitigation of licensing-based events. We started the process by putting together a series of white papers that built on some work in the prior DOE project called the Next Generation Nuclear Plant, which is a high temperature gas cooled reactor project. We started with the development of a paper to select and evaluate licensing basis events for use in the regulatory process. We had to write a white paper on how one does a PRA, because the PRA, first of all, had to be done during the design evolution of the plant, as well as capture different types of reactor technologies. We had a third white paper on safety classification of SSEs, and a fourth paper on defense in depth. These papers they have been converted into reports now, and they can be found on the NRC website that I covered earlier. They were reviewed first by an industry group organized by NEI that basically captures all the developing companies that are advancing these non-light water reactors. Then the NRC staff reviewed these, provided feedback. And as a result of all these 4 sets of white papers, we evolved a guidance document, NEI 1804, which has now been endorsed by the NRC in Regulatory Guide 1.233. The Regulatory Guide pulls out of these reports and white papers the part that's appropriate for NRC endorsement. But if you go back into the original reports, you'll see many more examples for existing technologies that were not really appropriate for an NRC endorsement. So that's a little bit of an introduction to the LNP process, and now I'm going to dive into the methodology itself. We designed this process to be risk informed and performance based. We get that by using quantifiable risk metrics to evaluate the plant, the licensing basis events, and the safety significance of the SSEs, the risk significance of SSEs. We use something called a frequency consequence target to evaluate individual licensing basis events. And then we also have cumulative risk targets to look at the overall integrated risks of the facility. We have the capability to quantify risk against the targets, and that helps to make it performance based. And then as the plants get built and operated, we keep track of the performance against the targets through the design and operational phases. We develop SSE performance targets that are tied to the reliability and capability of the SSEs in their roles in preventing and mitigating licensing-based events. And we select special treatment requirements for those SSEs that are all keyed towards meeting those targets. And then we have to put in place a monitoring program to make sure that the performance stays within the performance targets, and such that if they fall outside those targets, we can take corrective actions. to bring them back into performance. And we also identify risk margins against our performance targets, and that gives us one way to look at defense in depth. Licensing-based events is a very broad term here. They're broadly defined to include all the events that are used to support the safety aspects of the design and also to meet the various licensing requirements. They cover a comprehensive spectrum from everything from normal operation all the way down to rare off-normal events. We put them into categories. We have basically have four categories of license-based events. We have anticipated operational occurrences. We have design basis events. We have beyond design basis events and beyond design basis accidents. And I'll give you definitions of those on the next slide. We make use of work that was done in previous projects, so we didn't have to start with a blank sheet of paper when we developed this process. We have, since we're using terminology that in some cases is similar, in other cases different than the terminology used for the operating reactors, we include a glossary of terms. So we can be very clear about what we mean when we use key phrases like licensing-based events. We have 4 categories of licensing-based events. The first 3 categories are essentially event sequence families from a reactor and design specific PRA. And we categorize those in the first 3 categories based on frequency of occurrence. Events whose frequencies are greater than 10 to the minus 2 per plant year are anticipated operational occurrences. Those between 10 to the minus 2 and 10 to the minus 4 per plant year are design basis events, and events below 10 to the minus 4 are beyond design basis events. We cut those off at a little bit less than 10 to the minus 6 per reactor year, and I'll explain why in a little bit. We talk about frequencies on a per plant year, where a plant may be comprised of 2 or more reactor modules, as well as additional non-reactor radionuclide sources. And in the licensing-based event evaluation, we take on the multi-reactor risk head on. We don't play games with it like it's been played for the operating reactors. The last category, design basis accidents, are specifically designed to deliver the same kind of design basis accidents that are used in light water reactor licensing. These are deterministic animals. They're not tied to a specific frequency of occurrence, but we have a set of rules, reproducible rules, of starting with the other 3 categories and coming up with the design basis accidents, so that people in different teams and different technologies can consistently and reproducibly come up with a consistent set of design basis accidents for his or her reactor design and technology. So these DBAs are very similar to DBAs for light water reactors. They're basically events that only take credit for performance of required safety functions using safety related SSEs, and they have to meet dose limits that are tied to the dose limits in the regulation, which works out to about 25 rem TEDI, that's total effective dose equivalent at the site boundary. So those are the 4 categories of LBEs that we work with. The way we select and evaluate these, we organize the event sequences in a design and technology specific PRA into event sequence families. Event sequence families, basically you group together event sequences that have a similar initiating event, challenge to the plant safety systems, response to the plant safety systems, and end state. The reason why we have to deal with sequences versus families is that our PRA standards never standardize the level of detail for defining your event sequences in a PRA. There's different styles of entries out there. There's functional event trees and detailed event trees. There's risk man style of entries. So to capture to bring these things together in some kind of a normalized way, we group them into families, and there's formal definitions of families in the PRA standard. Then when we look at the individual LBEs, we look at them individually to see if they're risk significant using a frequency consequence target. And this is something new because normally in PRA and light water reactors, you're looking at the total risk using metrics like core damage frequency and large early release frequency. We do that kind of thing here, although using different metrics, but we also look at the risk significance of individual LBEs because one of the key functions of LMP is to select the licensing-based events. So we have to be able to look at them individually as well as collectively. We go through a process to examine what's behind the success criteria in all of our DBEs and high consequence BDBEs, and we work out something called what we call required safety functions. These are the safety functions that we need to preserve to keep our risk points inside the frequency consequence target. And then after evaluating what's available and not available through my event sequence families to perform those functions, the designer selects a package of safe-related SSEs to perform those required safety functions. And then after we figured that all out, we can go back and define the DBAs by taking the DBEs and modifying them by only taking credit for the safe-related SSEs and mitigation. So that's a thumbnail sketch of how we select and evaluate the LBEs. Using frequency consequence targets is something that goes all the way back to really the father of PRA. And by the way, it's not Norm Rasmussen, it's Reginald Farmer, who was working on these PRA techniques a decade or more before the original reactor safety study was done. He originally proposed a frequency consequence metric where frequency was measured like we do today, but the consequences in that case were measured by releases of iodine-131, which was a key radionuclide for those reactors at the time. There have been other attempts to do this. New Reg 1860, the technology inclusive framework, had a different approach to this. And in the LMP framework, we adopted this frequency consequence target. And it covers everything from normal operation all the way down to beyond design basis events. You can see the three categories of LBEs, the AOO region, the DBE region, and the BDB region. We want to keep the risks of our AOOs constrained by one of the regulations for normal operation, which is 10 CFR 20, which limits the annual releases, the annual doses from normal operation and frequent events to 100 millirem per year. So that's one criterion. We also we have the 1 rem PAG limit, which is the EPA protective action guideline limit for triggering an evacuation. We don't want to get into that for AOOs. We want to at least be in the DBE region for that. If we used a constant risk metric based on 10 CFR 20, you can see the dotted line that would be extended. But we also want to meet objectives for design basis events and beyond design basis events to satisfy the safety goals and other regulations. So this is the target that we use. And as you increase the ISO risk contours on this log plot would be diagonal lines that are indicated by those arrows. So increasing risk sort of goes northeast and decreasing risk goes southwest on this chart. So this is not a regulatory limit, it's a design objective. So the advanced reactor developers want to stay well inside this frequency consequence target. If they get within about 2 decades of this line, then the LBEs are considered risk significant. And while it's not a regulatory limit, everybody wants to stay inside the target. So that's That's the tool we use for looking at the risk significance of LBEs. We also have to look at the aggregated risks summed up over all of the LBEs, and we have three metrics for that. One's based on 10 CFR 20, which, as I mentioned before, limits the total aggregated releases from frequent events to basically 100 millirem per year over an entire year. So we have to make sure that's not exceeded. And then we have two criteria that come from the quantitative health objectives of the NRC safety goal policy to make sure that the individual risk for early fatalities within 1 mile of the site boundary is less than a given value, and the aggregated risks or the individual risk for latent cancer fatalities over a 10-mile region is led to another metric here. So those are our risk targets, and that's how we look at the risk significance of LBEs. We've had a lot of pilot studies where we've applied this methodology in various degrees, and the NRC website that I gave you earlier has copies of reports on just about all of these that you can go in and see how this whole methodology has been applied. The most complete examination to date is the VTR project. It's a new fast reactor that's going to be built in Idaho for experimental reasons, and it's based on the PRISM reactor technology. And they're doing a full implementation of VTR of the LMP process as we speak now. Some examples here. There was a project way back in the 1980s to develop a licensability prediction for the MHTGR, the modular high temperature reactor. And this is back in the late 1980s that this was done. They had a slightly different frequency consequence target back then, so their target looks a little bit different. But this is a good example of what we want to do with the licensing-based events. You'll see here you have these points on the frequency consequence target with uncertainty bands on them. These are 5th and 95th percentiles on an uncertainty distribution for both dose and frequency. And it just shows you examples of how the MHTGR licensing basis events worked out. You'll see up on the y-axis here, you'll see a bunch of points where you basically have no dose. This is a little bit, it's a little bit misleading because it shows that these doses are at 10 to the minus 7, but they're really at 0. But we want to retain zero consequence events so we can understand why are they 0? Why are the doses so low? And we take that insight into account in some of the application process. After we've done this part of the exercise to evaluate the risk significance, there's an important step where we work out what we call required safety functions. And these are functions that if we didn't fulfill them, or if we assume that they failed with a probability of 1, some of our DBE consequences could go beyond the frequency consequence target. Or if we had high consequence BDBEs, those are ones with the 25 rem or greater, they might increase in frequency and still go outside the target. So working out what those functions are is a very critical step in the LMP process, because those are the functions that you have to deal with when you classify SSEs as safety related. When we do the safety classification, it's not just the equipment like the pumps and valves and things like that, but it includes the identifying what features of the inherent reactor characteristics and the intrinsic reactor features have to be preserved to fulfill the safety case. And of course, it includes passive SSEs that perform their safety functions by passive means as well as active means, or combinations of the above. Most advanced reactor designs have different ways to perform these functions based on the redundancy and diversity built into their process. So normally the designer has choices as to what he wants to select to be safety related. The whole process of finding these is a very, very important part of this process. And conceptually, what we're trying to do is we're trying to see what functions are necessary to keep points well within inside the frequency consequence target, including all the ones that have zero consequence. And there's some fundamental thinking that goes behind these. It's not something that just manipulated out of a PRA model. Here's some of the required safety functions that the pilot studies have come up with. And the purpose of this slide is to show you that, we have the MHTGR and the XE100, which are both pebble bed high temperature reactors. No, I'm sorry, the MHTGR is prismatic high temperature reactor. The XE100 is a pebble bed HTGR. Prism is a sodium cooled fast reactor. Kairos has a fluoride salt high temperature reactor using coated particle fuel. And then we had the molten salt reactor experiment. This is the actual reactor that operated for some years at Oak Ridge, and the Westinghouse eVinci microreactor. So a point here is that the required safety functions are, first of all, tied to a source of radionuclides, and they're also technology specific. So that's just an example of how those things worked out. We developed the LMP process so that you can start with an internal events PRA and work through the process. And then later on, as the design matures and you know how you're protecting the plant against the external hazards, you can layer in the external hazards as well. But after you've worked out your required safety functions, even before you've done your external events PRA, you define what's called design basis external hazard levels, which is your design basis for protecting against external hazards. And you have to make sure you've covered all the external hazards down to 10⁻⁴ per plant year in terms of finding your design basis earthquake, your design basis wind speeds, external flood levels, and so forth. And then you have to put in a requirement that all your safety related SSEs have to be capable of performing their required safety functions in the event that any of these external hazards occur at that level. So by doing it this way, you pretty much, you enable the process to be implemented all pretty far through the process based on an internal events PRA. You can't really do the external events PRA until you know how you're protecting against them in the design. So later on, you'll layer these into the LBE process. So this shows that the application of the LMP methodology is in fact an iterative process. So to summarize the LBE part of this process, the AOOs, DBEs, and BDBEs are defined in terms of event sequence families from a design and technology specific PRA. A family has to be have similarity of initiating event, a challenge to the plant safety functions, response of those safety functions, and mechanistic source term if there is a release. We have a set of prescriptive rules for converting the DBEs into design basis accidents, where we're only taking credit for the safety related SSEs to perform the required safety functions. If you go back and look at the equivalent of the DBAs back in the PRA models, many times you will find that the DBAs correspond to event sequences modeled in the PRA that have in some cases extremely low frequencies, and the consequences of the DBAs evaluated using deterministic ground rules. Okay, so here's a stopping point. I'm going to talk a little bit about the PRA, a little bit about this, more about safety classification and defense in depth, but good stopping point here right now to field any questions you might have up to this point.
We had a question at the beginning from Ed. aside from heat pipe reactors, sodium or gas cooled reactors, what else is considered non-light water reactor?
Well, it's basically any reactor that deviates from the current existing light water reactor technology. So there's okay, some of the reactors sort of like in the transition zone, like NuScale small modular reactors. That's sort of in the twilight zone. It's really a light water reactor technology that's been organized into a small reactor technology. You could apply LMP to any reactor, including a light water reactor if you wanted to. But we're basically trying to account for reactors that have different types of fuels and different types of coolants and different containment strategies compared to regular reactors. I mean, the ones on the table now, the Avinci reactor is a micro reactor that uses heat pipes to cool it, which is kind of unique. Some of these reactors are graphite moderated helium cooled reactors. The Kairos design is a pebble bed reactor that's cooled with a fluoride salt. This is a sort of a salt type reactor. The molten salt reactors are homogeneous and heterogeneous. They could be thermal or fast in terms of the neutron spectrum. The homogeneous have the fuel dissolved in the coolant, in the salt coolant. And there's heterogeneous versions where you have the fuel separated from the molten salt. So it's basically anything that's out there, really. But those are the major. And of course, you had your sodium cooled reactors, and there's lead cooled reactors. Anything that departs from zircaloy clad UO2 water cooled reactors.
All right,
Okay.
we can move on. We'll take the rest of the questions.
Okay, good. So we'll go on to PRA development. In the LMP process, we encourage early introduction of the PRA in the design process. For a practical reason, you're going to have to do a PRA anyway to meet licensing requirements. The NRC requires PRA for new licenses. There's some glitches in the regulations that are being filled in right now, but it just won't be possible to license a new reactor in the United States without doing a PRA. Why not introduce it early in the process? Because the earlier you introduce it, you can incorporate risk insights in the design, which will lower the cost of the reactor compared to backfitting risk insights after you've already established the original design. When you put in the PRA in the early stage of design, you grade the scale and level of detail of the PRA model to be consistent with the level of detail and scope of the design information that you have. You can literally start a PRA with a single flow diagram and a few pages of text that describe your reactor, but it'll be very, very simplified PRA. As the scope and level of detail, your design information mature, the level of detail of the PRA goes along with it. But by doing this, the interaction between the PRA team and the design team, there's questions that go back and forth that on the one hand help the PRA analyst better understand the design, but help the designer understand what kind of issues will have to be faced with as the design matures. So it doesn't make sense to introduce hazards like seismic and internal fire and internal flood until you figured out how you're going to protect the plant from those hazards. So you have to have a minimum amount of design information on plant layouts and seismic design and so forth before you can do those hazards. The standard, the non-light water reactor PRA standard, specifically designed to support PRAs introduced at any stage of design. Now there's going to be limitations and uncertainties associated with the PRA, and they're dealt with in the deterministic defense in depth part of the evaluation, which will be the last part of my talk. There's been a lot of PRAs done for advanced non-light water reactors. I started my career at General Atomic doing PRAs on high temperature gas cooled reactors in the 1970s. Also, sodium-cooled fast reactors. There's been a lot of historical work done on sodium-cooled fast reactors. When you get beyond that, especially in the molten salt reactor area, the historical work on PRAs has been almost non-existent. So one of the things we try to do in the LNP process is to assist reactors with novel design to figure out how they could start putting together the building blocks of a PRA model. And there was some very interesting work done at Vanderbilt University under an EPRI contract to work out how to use things like process hazards analyses and HAZOPs to help the design, but at the same time put together the building blocks for a PRA model. And there's a whole PRA report that goes along with the LNP that provides guidance on how to do that. So I'm not going to go over the details of this, but if you go through the logic for how this is done, you can see how doing the PRA and the process hazards analysis with the design is a mutually beneficial thing. And it really reduces the overall cost of where you want to come out at the end point. We have a standard for advanced non-light water reactor plants that Mihai alluded to in the introduction. Talk a little bit about that. This standard makes use of the supporting standards on light water reactors. We've estimated that about 80% of the requirements in this standard are common to the requirements in the light water reactor standards. But we wanted to push the application of this standard well beyond where it's currently being used for operating light water reactors. So this standard addresses the whole suite of plant operating and shutdown states. The event sequences are developed all the way out to radiological consequence. So the scope is similar to a light water reactor level 3 PRA, although we don't use level 1, 2, 3 terminology in this standard, mostly because we don't use core damage, which is the interface between level 1 and level 2. We use technology inclusive end states and risk metrics, where we basically go all the way out to radiological doses and health effects. We do include sequences that may involve releases from 2 or more reactors or radionuclide sources. And we also have requirements for PRAs done at the pre-operational design stages. Because of the greater use of passive system reliability or the passive systems, we have requirements to address uncertainties in establishing the reliability of your passive systems. That's been benchmarked a lot in the recent PRISM PRA. And we're consistent where we need to be with the supporting LWR standards. We started the working group in 2006, and I've been the chairman ever since. I just passed the baton on to David Grabaskas today in a meeting we had earlier today. In 2013, we issued a trial use standard, and that then was piloted on many different pilot PRAs. The first pilot was the HTR PM that was built, the pebble bed reactor that was built in China, and it was actually used to help license the China pebble bed reactor over there. In 2018 to 2020, we made revisions to our standard to address feedback from pilot studies. And we had to go through 2 cycles of standard ballots with the Joint Committee on Nuclear Risk Management. And on the first recirculation ballot, or the second ballot, we got unanimous approval of the standard. So that happened last summer. We had to go through a 60-day public review comment period where we actually received no comments, which is typical. But then it had to be approved by various boards, including the standards boards at ANS, ASME, and ANSI. That's the American National Standards Institute. So this latest standard which will be ASME ANS RAS 1.4. By the way, that's a misprint, should be 1.4. 2021 will be the standard number. And that should be coming out in the next couple of days. You'll be able to get this from ANS or ASME. I'm not sure how much they're going to charge for it, but it's the largest standard in terms of size of any standard ever issued by ASME or ANS. About 500 pages of requirements. The NRC plans to issue a regulatory guide to endorse the standard for use in licensing advanced non-light water reactors. And it'll have one set of endorsement for plants that are following the LNP process. But the LNP process is optional. You don't have to follow it if you don't want to. It's one acceptable way to move forward with your license, but you're still going to have to do a PRA anyway, and that'll be addressed in the guideline. There's some terminology differences that we had to introduce in our standard and they all had good reasons behind them. We don't use core damage frequency because we don't use core damage. Core damage is actually technically defined in terms that are really only applicable directly to light water reactors. They refer to the oxidation temperatures of zircaloy, the melting temperatures of UO2, and things like that, water levels in a reactor vessel. And none of those definitions of core damage really apply to any of the non-light water reactors. So we don't use a core damage frequency. Large release frequency, large early release, we could use those because they're really defined in terms of how much radionuclide releases take place, but we don't need them in our standard because we take the consequences all the way out to dose. So we don't have to arbitrarily assume that if you go above this limit, it's large or early. So it's we don't use any of those metrics because they're either not applicable or we don't use them. We use terminology event sequence versus accident sequence. LWR PRAs are only looking at beyond design basis accidents. That's all they look at. Because success dates they don't really talk about anything other than success. But we want to use the PRA to select our licensing basis. So our event sequences include normal operation, anticipated events, beyond design basis events, and so forth. So we don't use accident sequence, we use event sequence. And we use the term reactor coolant boundary. We don't use pressure boundary because some of these reactors are pool type reactors at atmospheric pressure, so they don't necessarily have a pressure function. But they all have boundaries, and we talk about breaches. Containment in the light water reactor world is a building, a leak tight building or structure. We don't really use those in non-light water reactors, but we translate those requirements to barriers, radionuclide transport barriers, and we can have bypass of those barriers and so forth. So anyway, these are some of the terminology differences that we use. When we organize our PRA requirements into technical elements, it comes together in this chart here. We have 18 technical elements, and it goes from plan operating states, and initiating events and so forth, all the way out to integrating risk, where in this case, we include mechanistic source terms and radionuclide consequences, as well as event sequence frequency quantification in the overall risk. The pilot studies, this is a table of all the pilot PRAs that were done based on the original trial use standard. So we had a lot of different types of reactors apply this at different levels of detail. So we pretty much demonstrated that our standard is applicable to all the different advanced reactor concepts out there. Lessons learned from the pilots. There was a very strong consensus that our standard was useful in establishing the adequacy of PRA for their reactors. We got the best feedback from 3 pilots: the PRISM pilot, the HTRPM in China, and the TerraPower traveling wave reactor. There was a lot of feedback in improving our treatment of risk significance, and we had issues dealing with very small frequencies and very small doses and how to deal with those. And we wanted to bring in both relative and absolute risk importance measures for risk significance. As I showed you earlier on, we actually use absolute risk importance metrics for the LMP process. So anyway, that was the lessons learned. We found that we learned enough to proceed. Any questions on the standard while we're at this point? Okay, I can see we're running short of time here. Talk a little bit about safety classification. I told you about the safety-related SSEs. We've already covered that. We needed to define those in order to derive our design basis accidents. We have a middle category called non-safety related with special treatment, where we look at the non-safety related SSEs and we ask ourselves, do they meet certain risk significance criteria, or are they perform functions that are deemed necessary for adequate defense in depth? And then if we don't end up in NSRST or safety related, then we have everything else, which is non-safety related with no special treatment. So those are the 3 categories that we use. The safety related, this is just another statement of what was in the chart. So we have clear criteria for getting into safety related based on managing our DBEs inside the frequency consequence target, and the safety related with non-safety related with special treatment gets in there via defense in depth or risk significance. The risk significant criteria, we look at functions that might be necessary to keep some of the LBEs inside the frequency consequence target. And we also have criteria based on a roll-up of all the event sequences where the SSE has failed to see if it comes within 1% of the cumulative risk metrics. So those are the different ways in which an SSE can be risk significant. Notice that these risk significance criteria are based on absolute limits, an absolute frequency consequence target, and absolute cumulative risk targets. This can be contrasted by using things like Fussell-Vesely and risk achievement worth, which are always baselined on your variable total integrated risk. So this was a game changer in terms of changing the whole idea of what we mean by risk significance. It's a Venn diagram that sort of shows the sample space of all the plant SSEs. Some of them are modeled in the PRA. A subset of those are found to be safety significant. That means they're either safety related or risk significant, or they're necessary for adequate defense in depth. And this is what how the Venn diagram sort of lines up. After we've done our safety classification, where the rubber meets the road on cost is the special treatment requirements. So for the safety-related SSEs, we take the required safety functions and develop something called required functional design criteria. And those end up being the principal design criteria that you need to put in your license application. And then we have specific design criteria for our safety-related SSEs. For the safety-related and NSRST SSEs, we set numerical targets on the capability and reliability of the SSEs in the performance of their functions. And these targets are linked into the LBEs that gave birth to the classification. We focus on the prevention and mitigation functions of those SSEs and the LBEs. This is kind of similar to the process that's in 10 CFR 5069, where the operating reactors are trying to backfit risk insights into their safety classification. The difference here is that we're forward fitting the risk insights from the get-go. So we're not going to have, for example, safety-related SSEs that are not safety significant. Probably takes some more time to get into this, but if you go into the SSE white paper behind LMP, you can see that when we talk about SSE functions coming out of the NRC world, they want to have a balance between prevention and mitigation. And normally when the NRC talks about that, they're talking about preventing and mitigating core damage in a light water reactor. We needed to have a more fundamental and global way to talk about prevention and mitigation. So what we do in this chart is that we look at the roles of the SSEs, and on the sequences in which they work, their ability to mitigate or eliminate or reduce dose is a metric we can use for their capability. And when we look at the sequences where they fail, their failure probability is a metric that enables us to look at them preventing more serious accidents. So when we go through these special treatment process, we want to ask ourselves, okay, what are we doing with the special treatment? Are we trying to work on preventing something and therefore we're worried about reliability, or are we worried about mitigating something? So we have to look at the safety margins and its ability to mitigate accidents. These fundamental questions were kind of mixed up in the LWR special treatment requirements. So on the safety classification, we build on prior work in the DOE's safety classification process. We have two categories of safety significant SSEs, that's safety related and non-safety related with special treatment. We have absolute metrics for risk significant, which is a departure from light water reactors. We develop special treatment requirements in the formulation of reliability and capability targets. Quality assurance, is a graded process. In this process, we apply the regulatory limits of Part 50, Appendix B, QA on safety-rated SSEs, and then we use less rigorous QA for the remaining components. So that's sort of the overall summary. I see we're running pretty close to out of time here. I just want to make a few comments on the defense in depth approach. We use a sort of a triangle process for looking at defense in depth. The lower left of the triangle is talking about the plant capabilities for defense in depth, the use of multiple barriers, the use of redundancy and diversity, things that are physical manifestations of not relying on a single physical element of design. On the lower right, we have the programmatic defense in depth, which are the programs we put in place to provide greater assurance that the plant capabilities will be realized. And at the top, we do a risk-informed performance-based evaluation of the defense in depth. I knew we were going to have some challenges here to get through this all this material in an hour period of time, but we're very proud of what we were able to accomplish in the LMP process. We have a structured, systematic, and reproducible process for selecting and evaluating licensing-based events, for safety classification of SSEs, for developing performance targets for reliability and capability, and for incorporating defense in depth principles into the decisions. The whole goal is to contribute to consistency in the preparation of successful licensing applications and eliminate this barrier that used to exist that inhibited the advancement of non-light water reactor technologies. So that's it. I've used up the whole hour, but I'd be happy to hang on here for additional questions.
Thank you, Karl. So we have a couple of questions in chat. I'm going to start with the earliest one. What's the basis that LBEs can be screened out during the grouping of event sequences?
Yeah, the non-light water reactor PRA standard has very well-defined screening criteria for screening out event sequences, hazards, systems, basic events, or whatever. And basically, the screening criteria are structured in such a way that you have to develop a case that had you included them, it wouldn't result in a risk significant item in your model. So but even though we have screening criteria, when you screen things, it doesn't mean they go away. It just means that they're in that part of your PRA that covers the screening process. When you update your PRA for the next stage of design, you have to go back and revisit those screen items to make sure that the screening criteria are still met. So that's basically the way we do it.
Next question. Since VTR is regulated by the DOE, is its use of the LMP process being used as a test bed for how the NRC might use the process in the future?
Well, it's I think first of all, in applying the LMP process to the DOE, they have a different. They don't license the DOE reactors. They have an authorization process. They have slightly different frequency dose limits. So the frequency consequence target was adapted to meet the DOE frequency dose limits rather than the NRC dose limits. So they don't use the same exact process. But, you know, I think that the idea of, well, first of all, DOE has been behind the LMP process, and merging this project where they needed a new reactor, a fast neutron spectrum test reactor to make neutrons and to accelerate irradiation experiments beyond what they could get from thermal reactors. They decided they would kill two birds with one stone and advance the LMP process while setting the stage for a new test reactor. So I think that DOE had common interests here. They had common interest to advance reactor technology commercially, as well as do the DOE job of providing a new test reactor.
Yep, thank you. One last question before we end. Are the PRAs peer reviewed to ensure a level of quality, and is risk data available from foregone designs and plans? Using process safety management concepts is a great initial step.
Yeah, so yeah, first of all, as far as let's see if I understand the question. I'm sorry, could you repeat the question? I sort of lost.
Are the PRAs peer reviewed?
Oh, yeah, okay. Yeah, there are requirements in the PRA standard to conduct a peer review. That's similar to what's the case for operating reactor PRAs. So there are peer review requirements, and they're very similar between the non-light and light water reactors. And there's NEI is now developing a new PRA peer review guideline for conducting peer reviews that's similar to the one that they had already developed for light water reactors. So it's focused on the main difference in the peer reviews for this reactor is that when you get a review team put together for a new non-light water reactor PRA, you're not going to have the luxury of having people that are knowledgeable about the technology and knowledgeable about PRA. So there's a little bit of training required to train the peer review team in the safety design approach associated with the reactor, so they know how the PRA processes have been adapted to that technology.
Thank you. An associated question, is risk data available from foregone designs and plans?
Yeah, each technology has a different story there, but there is in one of the documents available on the NRC website, there's an FAQ document, frequently asked question document. And one of the questions that comes up is, where do you get the data for doing your non-light water reactor PRA? And so that's on there. Each reactor technology has developed different levels of data. Gas-cooled reactors have benefited from gas-cooled reactors in England, Magnox and advanced gas-cooled reactors, and some limited number of HDGRs. The sodium-cooled fast reactors have similar legacy, and they've actually, Vanderbilt has actually put together a database for use on process plants that comes from some of the DOE facilities. One thing I always like to remind people of is that when Rasmussen did the first PRA of light water reactors, no one had developed any light water reactor specific PRA data. That data was culled together from industrial sources and from generic sources and non-nuclear sources. For example, gas pipeline data and steam plant data was used to come up with the original LOCA frequencies for PRAs. So there is data out there. There's larger uncertainty because of less operating experience, but we, in the light water reactor world, we suffered from that back in the 1980s. So it's not a showstopper, but you just have larger uncertainties.
Yep. All right. Well, one very last question. There are increasing uses of digital control and management systems in advanced reactor designs. How do we plan to consider the safety of digital systems in the safety analysis of advanced reactors?
Yeah, that's a good question. And fortunately, we can benefit to some extent from some work that's already been done for light water reactors, because they've already been backfitting digital INC systems onto operating light water reactors. And of course, they've introduced those for all the advanced reactor designs. So our digital INC approach basically is building on that. What you have here is a lot of operating experience with very few failures. There's a lot of emphasis on how you treat common cause failures with digital systems. But again, this is something that's not new and unique to non-light water reactors, but it still has to be addressed. One of the technologies that's been under development, which I'm not at liberty to give you much details on, but they are, some reactor developers are working on reactors that have no operators. They basically are operated with robots and automated systems. So the whole question of human reliability analysis is something that will have to be rethought. But these kinds of things are finally solved through experience and actually doing the work. So
thank you very much.
When I started my career, nobody knew how to do common cause failure. So we figured, we looked at some data, we figured out some models, and we moved on. Low power shutdown PRA, same thing. So we have challenges, and smart people from North Carolina State will probably come up to the plate and figure out how to do it.
Thank you. Thank you for a great talk, very informative. If you have any other questions, please reach out to me or Karl directly. If you want to have the slides, I have them. So you have my email address. You can all reach out to me. Thank you very much, everyone. I'll see you next week.
Thanks a lot. Appreciate the time.
Have a good night.